Welcome to NEET Fast Forward, Work, Energy and Power, Part 1. Work done by a force F in displacing a body is given by W is equal to F dot X, or that is equal to Fx cos theta, where X is the displacement, theta is the angle between force and displacement. This work done can be equal to 0 also. If F equal to 0 or X equal to 0 or cos theta equal to 0, means theta equal to 90 degree. In all these cases, work done will be equal to 0. Work done will be 0 if force equal to 0 or displacement equal to 0 or theta is equal to 90 degree. Angle between force and displacement is 90 degree. Work done by a force can be negative or it can be positive also. Say for example, here there is an object, say there is a ball which is taken to a height h. A ball is taken to a height h. Okay, mass of the ball, let it be m. What is the work done by the applied force? Applied force, say applied force, let it be mg. Mg is the applied force. Displacement is upwards. Applied force is also acting upwards. Displacement is also upwards. So mg into h. Angle between force and displacement is 0 degree and cos 0 will be equal to 1. So work done by applied force is equal to mg into h. But what about work done by gravitational force? Work done by gravitational force, okay, work done by gravitational force equal to, when you are lifting the body upwards, gravitational force was acting downwards. Gravitational force is equal to mg. Displacement is upwards. Angle between gravitational force and displacement is 180 degree. Cos 180 is minus 1. So work done by gravitational force is minus mgh. Okay. When you lift a ball upwards and if you give a displacement h, work done by the applied force is positive and the work done by the gravitational force is negative. Similarly, if I move this ball from a height h to the ground, then when you are bringing the ball downwards, applied force is upwards only. Okay, work done by the applied force is equal to, because see, you are moving this ball downwards. Okay, so if you leave the ball will fall down. So you have to apply a force on the ball upwards only. Okay, so applied force is mg, displacement is h. So applied force is upwards. Even though the mass is coming down, applied force is upwards. Otherwise, ball will be under free fall. Okay, and the displacement will be downwards. So angle between them is 180 degree. Cos 180 is minus 1. So work done by the applied force is minus mgh. But what about work done by gravity? Work done by gravity is gravitational force is acting downwards. Your displacement is also downwards. So therefore, angle between force and displacement will be 0, cos 0 equal to 1. So work done by gravitational force is positive, plus mgh. Now we'll see how to calculate work done. If the force is varying linearly, Okay, if the force is varying linearly, say let us suppose that a force f of x varies with the displacement like this. So there is a linear relationship between force and displacement. So then, okay, say this is the initial displacement. Okay, so this is x2 final position. Now here the force, let it be F1. So here the force, let it be F2. So in this case, how to calculate work done? Work done equal to average force into displacement. Okay, say in this process the displacement is x2 minus x1. So let me take displacement x2 minus x1 equal to some s or x. Okay, so what is average for? Work done will be equal to f1 plus f2 divided by 2 into x. So this is how we have to calculate work done. But whereas in the case of variable force, okay, if the force is variable, say this is how force varies with the displacement. Say this is how the force varies with displacement. Here I have a variable force. When there is a variable force, what I should do? Okay, I should divide this area into many pieces. Okay, so then I should integrate. Okay, I should add all the areas of these rectangles. Okay, so if there is a variable force, how to find out work done? So work done will be equal to integration of force. Okay, integral of force over displacement between initial and final position. So this is initial position and this is final position. You see here the force is varying. Okay, force is it is not linearly increasing. So in this case, here force was linearly increasing, so we took the average. So here it becomes very difficult for us to take the average. So what we have to do actually, area under force versus displacement gives work done. Okay, so how to do? We have to divide this area into many rectangles, then we have to add the areas of all these rectangles, then we will get area under the curve. So that is mathematically given by work done is a definite integral of force over displacement. Then we will calculate work done by spring force. So spring force is an example for variable force. Let us suppose that we will see what is the expression for work done by spring force. Expression for work done by spring or work done by spring force. So let us suppose that I have a spring mass system here. Okay, so here there is a spring and here there is a mass connected. Say this surface is smooth and this is the equilibrium position of the spring. So now spring is given some, we have applied some force on the spring. So this is the displacement of the spring. Say the displacement of the spring is x. So displacement was in this direction. Okay, so this what the spring will do, spring will try to pull the block backward. So this will be the direction of spring force. So from Hooke's law, so we know that force is directly proportional to extension produced in the spring, or force is equal to a proportionality constant k into x, where this negative symbol indicates that force and displacement are in the opposite direction. F is equal to spring force is equal to minus k into x. Now how to calculate work done? Now we know as the extension increases here, spring force also increases. So here there is a variable force. So work done is equal to integration of okay, f dot dx between the limits xi and xf. So work done is the definite integral of force over displacement. Now what we'll do, angle between displacement and spring force. Displacement, block is being displaced forward, spring force is pulling the block backwards. So angle between them is 180 degrees. So I'll write minus here. So minus integration of what is f? F is equal to minus kx into dx. Actually, how I should write? F into dx into cos 180. Cos 180 is minus 1. That minus 1 I have written here. And in the place of f, I have written minus kx. So between the limits 0 to x. So this was the equilibrium position. X is equal to 0. Now here extension is equal to x. Okay, from 0 to x, what is the work done? We have to calculate. So what happens? So this will be equal to this minus minus gets cancelled, k into integration of x with respect to x between the limits 0 and x, or that will be equal to w equal to k into, so integration of x power 1 is equal to x power 1 plus 1 divided by 1 plus 1. It will be x square by 2 between the limits 0 and x, or I can write work done by spring force is equal to half into kx square. Work done by spring force is given by half kx square. Here if the extension, okay, if the extension changes from x1 to x2, then if the extension changes from x1 to x2, then what happens? Then work done by spring force is given by half into k into x2 minus x1 whole square. X2 minus x1 whole square. When the extension changes from x1 to x2. When the spring goes from 0 to x, it is simply half kx square. When actually the originally if the extension is x1 and then the later extension will be x2, then the work done is given by half into k into x2 minus x1 whole square.